A lot of you might have made this mistake before. A plus b squared equals a squared plus b squared, or in general, a plus b to the power m equals a to the power m plus b to the power m. This is famously coined freshman's dream. Now we of course know that this is wrong in general, but it isn't completely wrong. In some cases it could be correct. One very easy example is where a or b is 0. Then both sides are a to the power m or b to the power m, so the equality obviously holds. Mathematicians like to call those trivial or degenerate cases because they are not interesting. The more interesting case involves modular arithmetic. Technically, we don't have equality but a congruence relation. However, since the congruence works pretty much like equality in modular arithmetic, we count it as a special case of the freshman's dream. There is another video where I explained many elementary modular arithmetic concepts, and it will be shown in the card above. Here is a crash course. If you see a congruent to b modulo m, that means a minus b is divisible by m. The congruence is in the sense that when a and b are divided by m, their remainders are the same. We now consider a positive integer a prime number p, which is co-prime with a, and this list of multiples of a. Consider the remainders when these multiples of a are divided by p. It could only be 0 to p minus 1, but 0 is not possible here. Why? If, say, I times a leaves a remainder of 0 when divided by p, that means p is a factor of I times a. A doesn't contribute the factor p as they are co-prime, and neither does I, because it is less than p. So 0 is not a possible remainder here. In addition, no two numbers on the list should leave the same remainder when divided by p. Let's say I times a and j times a are the two numbers. Then j minus I times a is divisible by p, which contradicts what we discussed a moment ago. So every number on this list has a unique remainder from 1 to p minus 1 when divided by p. So now if we consider the product of these numbers, their remainders should also multiply. So we have p minus 1 factorial times a to the power p minus 1 congruent to p minus 1 factorial modulo p. Since p minus 1 factorial is co-prime with p, we can cancel them from both sides. This end result is called Fermat's little theorem. In this result, we can multiply both sides by a to get a congruence relation that is true even if a and p are not co-prime. So a plus b to the power p is congruent to a plus b modulo p, and a to the power p plus b to the power p is also congruent to a plus b modulo p. So a plus b to the power p is congruent to a to the power p plus b to the power p modulo p, which is the correct version of the freshman's dream. This mistake committed by a lot of people could in some sense be right. If you enjoyed this video, give it a thumbs up and share it. Be sure to subscribe with notifications on. See you on the next video. Bye!